Alright, in today's video, I'm going to be going over higher order derivatives, so let's get into it. So what is a higher order derivative? So it's basically a derivative that you get by differentiating a function multiple times. So what I mean by that is, let's say you have a function f, and then you take a derivative. Then you get f prime. This is the first derivative of f. But then what happens if you differentiate the derivative? If you take f prime and you take a derivative, you get the second derivative of f. And what you use is, instead of having one apostrophe, you have two to show that it's the second derivative. Now, if you can keep going. If you differentiate the second derivative, you get the third derivative. So you can do triple prime, or you can do f and then superscript 3 with the little parentheses there. And then you can keep going. Eventually, if you differentiate the n minus 1 derivative, you get the nth derivative. So basically, you can keep going with derivatives. You don't have to stop after 1 or 2. So let's do some practice. Alright, so we're starting off a little bit easier. So our f is 16x to the fifth minus 3e to the x plus natural log of absolute value x. Alright, so if you differentiate f one time, you get the derivative of all of that business. So let's go term by term. The derivative of 16x to the fifth, that's 80, and then we bring the power down by 1, x to the fourth, and then minus 3, e to the x just differentiates to itself. And then the derivative of the natural log of absolute value x is 1 over x. I'm going to write that, just because we have to differentiate again, I'm going to write that as x to the negative 1, because we're going to need the power rule. So now, to get the second derivative, f double prime, you just differentiate this again. So the derivative of 80x to the fourth, that's going to be 320, and then you bring the power down, x to the third, negative 3e to the x, that's just negative 3e to the x when we differentiate that. And then by the power rule, the derivative of x to the negative 1 is negative 1x to the negative 2. So let's write our final answer. 320x to the third minus 3e to the x minus this negative 1x to negative 2. We can bring that negative 2 power down to the denominator. So that is our final derivative. All right. All right, for the second problem, we need to differentiate 4 sine of x minus 12x squared twice. So for our first derivative, the derivative of 4 sine x, that's for cosine of x, because sine differentiates to cosine. And then minus 12x squared, we use our power rule, so that would become minus 24, because we multiply the negative 12 and the 2, x to the 1, so just x. Now we differentiate once more. So the derivative of cosine of x is minus sine of x. So the derivative of 4 cosine of x is negative 4 sine of x. And then negative 24x differentiates to negative 24. So that is our final derivative. All right, now for some practice that's a little bit harder. So we have 6e to the negative 2x, and we want to differentiate that 4 times. Now, we could do it individually each time, but that's going to be a little bit too tedious. If you notice, the derivative of e to the negative 2x? Well, we do the derivative of the outside function, which is e to the x, and then that's just e to the x, but we replace that with e to the negative 2x, multiplied by the derivative of the inside, which is negative 2. So that's negative 2e to the negative 2x. If we do that again, it'll be the same thing, but we just get another power. Let me write it out. If we differentiate that again, we'll just get another power come down of negative 2. And in general, if we differentiate it n times, we're going to have negative 2 to the nth power, because we're going to have n of them, e to the negative 2x. So what I'm saying is after 4 derivatives, we should, since we're just repeating the chain rule again and again, have 4 multiplications of negative 2. Let me get rid of this. Notice that we do have a 6 out in front. That doesn't really change anything, because it's just gonna stay out in front when we take the derivatives. So f and then 4, the fourth derivative of f, that's gonna be 6 times, we're differentiating 4 times, so we're gonna have 4 powers of negative 2. So negative 2 all to the 4th power, that's 16. And then 6 times 16 is just 96. And then e to the negative 2x. Alright, for this next problem, we're going to use a fact about trig functions, specifically sine and cosine, that is going to make this a lot easier. So the 19th derivative of sine of 2x, that's kind of ridiculous to do one by one. So let's look at what happens when you're just having normal sine, and then you differentiate that. That goes to cosine. Alright, and then if you differentiate that again, you get minus sine. Again, you get minus cosine. And once more, you just get sine. So doing 4 derivatives just gets you back where you were. So for this reason, we can actually take off multiples of 4 from this g, the 19th derivative of g, and it will be the same thing. Now that's ignoring this 2x on the inside. We know, if we just look at the first derivative, we know that we're going to have the derivative of the outside value at the inside, so cosine of 2x, multiplied by the derivative of the inside, so 2 cosine of 2x. If we keep doing that again and again, because we just have that 2x on the inside, that's going to keep differentiating to 2 again and again. So for n many derivatives, we're going to have a 2 to the nth power, because that's how many times we're multiplying that 2 out in front. But keeping that in mind, this is actually going to follow a very nice pattern. So instead of taking the 19th derivative, we can go with 15. We're subtracting 4. We can go from 15 to 11. And then from 11 to 7. And then finally, we can go to 3. Oop, not negative 3. We can go to 3. So ignoring what's on the inside, this is actually going to be the same. This 19th derivative is going to be the same kind of function as the third derivative. Well, what is the third derivative of sine? We know sine goes to cosine. Cosine goes to minus sine. If you take another derivative, the third derivative, you get minus cosine. So we know from earlier, we said we're going to have a 2 to the 19th power, because we're doing 19 derivatives, and by the chain rule, we're just going to multiply that 2 19 times. And then multiplied, we said negative cosine of 2x. So our final answer is negative 2 to the 19 cosine of 2x. So sometimes with these problems, you can use kind of symmetries and some shortcuts to do it. If you did this by hand, one by one, it would be a lot of work. So you can kind of use some little tricks to make it easier. All right, let's move on to the next one. All right, so one more problem. So what's the nth derivative of a to the x? So our function is f of x equals a to the x. Let's just see what happens when we differentiate one time. So the first derivative, we know that f prime. So what's the derivative of a to the x? That's just natural log a multiplied by a to the x. Okay. Now the second derivative. So we have this natural log a out in front. We can just keep that out in front, didn't change anything. And then the derivative of a to the x, we already said that was natural log a to the x. So now we have two natural log a's. So this is natural log a squared a to the x. Let's just do one more just to see. So the third derivative of f of x, well, we're going to differentiate a to the x again, and then we just have that natural log a squared out in front. We know the derivative of a to the x is just natural log a to the x. So now we have 3 powers of natural log a when we have the third derivative. So it seems like what our pattern is showing us is that the nth derivative of f of x equals a to the x is going to be natural log of a to the nth power multiplied by a to the x. So that is what our pattern is showing us. So our final answer is natural log a to the nth power multiplied by a to the x. Alright, thank you for watching the video. In the next video, I'm going to be going over some implicit differentiation. And then I think soon after that, I will be going over some applications of differentiation. Anyways, thank you for watching once more, and have a great rest of your day.